Now we are going to the Laplace transform of polynomial. That means t to the power n is non-negative integer. Okay. Now let's recall the definition of Laplace transform. Laplace transform of a function of t equals to integration from 0 to infinity of e to the power minus st into f of t with respect to t. Okay. Now here f of t should be t to the power n. Okay. So Laplace transform of t to the power n will be integration from 0 to infinity of e to the power minus st into t to the power n with respect to t. Now we can denote this equation as star equation. Now we evaluate this integral. This integration of e to the power minus st into t to the power n with respect to t. This integral should be done by integration by parts method, integration UV method. Okay. In integration UV method, integration by parts, polynomial function should be u and exponential function should be v. Okay. So this integration would be t to the power n integration e to the power minus st with respect to t minus ddt of t to the power n integration e to the power minus st with respect to t, then the whole integral with respect to t. Okay. Now integrating e to the power minus st, we get minus 1 by s e to the power minus st. Okay. Minus this derivative is n t to the power n minus 1 and this integral is minus 1 by s e to the power minus st and then the whole integral. Okay. Now we get minus t to the power n by s e to the power minus st. This minus and this minus will multiply and we will get plus n by s integration e to the power minus st into t to the power n minus 1 with respect to t. Okay. Now we will plug in this information to star equation. We will replace this information. We will use this information to the star equation. So the star equation becomes Laplace transform of t to the power n equals to, in here we can replace this part, but here limit is concerned, so we will replace this part with limit from 0 to infinity. So minus t to the power n by s e to the power minus st from 0 to infinity, then plus n by s integration from 0 to infinity e to the power minus st t to the power n minus 1 with respect to t. Okay. Okay. We can add a constant here. We can add a constant here because this integration is indefinite, but this constant has no contribution in this calculation because this is a definite integral. So we will neglect this constant in the star equation. Okay, so this constant is negligible here, but In indifferent integral, constant is needed. Okay, but this constant has no contribution in the star equation. Okay, now look at this portion. This portion is Laplace transform of t to the power n minus 1, because Laplace transform is defined by this equation, and here f of t is t to the power n minus 1. So we will write this part as Laplace transform of t to the power n minus 1. Okay, and this part will be minus t to the power n by s e to the power minus st. Okay, now we will remove this portion. We'll remove this portion and we will highlight this equation. Laplace transform of t to the power n equals to minus t to the power n by s e to the power minus st from 0 to infinity plus n by s Laplace transform of t to the power n minus 1. So this equation we will call double star. Okay, now we will evaluate this portion. We will find the magnitude of this portion. So we are going to the minus t to the power n by s e to the power minus st from 0 to infinity. We are going to this part. Now by putting limiting value we get minus limit of, by putting the limit value infinity we get minus limit of t to the power n by s e to the power minus st, t tends to infinity, then minus and minus multiply and we will get plus 0 to the power n by s e to the power s into 0. Okay, now this part is 0 by something, so 0. Now we are getting to this part. Okay, limit t to the power n by s e to the power st, t should be infinity. Okay, t approaches infinity. Now we use the exponential series. The exponential series is one plus st by factorial 1 plus st square by factorial 2 plus st cube by factorial 3 plus and so on. Okay, we will get st to the power n minus 1 by factorial n minus 1 plus st to the power n by factorial n plus st to the power n plus 1 by factorial n plus 1. Okay, plus st to the power n plus 2 by factorial n plus 2 and so on. Okay. Now we will take t to the power n into denominator, and we will write 1 over s 1 by t to the power n plus s by factorial 1 t by t to the power n plus s square t square by factorial 2 t to the power n plus s cube t cube by factorial 3 t to the power n plus s to the power n minus 1 t to the power n minus 1 by factorial n minus 1 t to the power n. Okay, then s to the power n t to the power n by factorial n t to the power n plus s to the power n plus 1 t to the power n plus 1 by factorial n plus 1 t to the power n, then s to the power n plus 2 t to the power n plus 2 by factorial n plus 2 t to the power n, and so on. Okay. Now we will simplify each and every term in the denominator. This term should be, this part will be t to the power n minus 1 in the denominator of this term. So this will be t to the power n minus 1, and this will be, this part will be t to the power 1 by t to the power n minus 2. That means we will write 1 by t to the power n minus 2. This part we will write 1 by t to the power n minus 3. Okay, 1 by t to the power n minus 3. This part will be just 1 by t. We are simplifying. Okay, and this part, in this term t to the power n are cancelled. In this part t, only t will be present. In this part t square present. Okay, and so on. Now apply this limit. When we apply this limit, we will get this part as 0, this part 0. So from here to this part we will get 0 0 0 0 0 0, and this part will remain unchanged because there is no t in s to the power n by factorial n, and then t should be infinity, t square should be infinity. So this portion will approaches infinity because t approaches infinity. So this portion is approaching 0, this part or this term is unchanged, and this portion approaches infinity. So we are getting minus limit of 1 by s into this part 0 plus s to the power n by factorial n plus, and this part s to the power n plus 1 by factorial n plus 1 t plus s to the power n plus 1 by factorial n plus 2 t square t tends to infinity. So this part is infinity, approaches infinity. Infinity plus something will approach infinity. So total part or full fraction will approach 1 by infinity. So 1 by infinity is 0. So we got the magnitude of this portion, and the magnitude is 0. Okay. Now we replace the result in the double star equation. So therefore, from double star we get Laplace transform of t to the power n equals to 0, this magnitude is 0, plus n by s Laplace transform of t to the power n minus 1. Okay. Now take this equation. This equation is recursive. Why? Because when a function is defined by itself, then the decision or the definition is recursive. So this equation is recursive because this is defined by itself. This is Laplace transform of t to the power n, and this is Laplace transform of t to the power n minus 1. Now we will remove the upper portion and now we will write or we will highlight this equation. Laplace transform of t to the power n equals to n by s Laplace transform of t to the power n minus 1. Okay. Now Laplace transform t to the power n minus 1, we can get this by replacing n as n minus 1. So Laplace transform of t to the power n minus 1 is n minus 1 by s Laplace transform of t to the power n minus 2. Okay. And then Laplace transform of t to the power n minus 2 equals to n minus 2 by s Laplace transform of t to the power n minus 3 and so on. Okay. Now this equation we can denote as triple star equation, and from this triple star equation we get Laplace transform of t to the power n equals to Laplace transform of t to the power n equals to n by s Laplace transform of t to the power n minus 1, and here we will substitute Laplace transform of t to the power n minus 1 result, and that is n minus 1 by s Laplace transform of t to the power n minus 2. So we will substitute here n minus 1 by s Laplace transform of t to the power n minus 2. Okay. Now we will substitute Laplace transform of t to the power n minus 2, and that is n minus 2 by s Laplace transform of t to the power n minus 3. So n by s into n minus 1 by s into n minus 2 by s Laplace transform of t to the power n minus 3. Okay. Now take a point that power of t is 1 less than, power of t is 1 less than the last factor. Here last factor n minus 2 and the power of t n minus 3. Here the last factor n minus 1, power of t n minus 2. So the power of t is 1 less than the last factor. So propagating in this way, we will get one, because n is an integer, in fact non-negative integer, and by subtracting 1 1 1 1 we will get 1. So when the last factor is 1, then Laplace transform of t to the power should be 1 less than last factor. Here last factor is 1, so power would be 0. Okay, and this 1 over s, of course, because every factor over s, every factor over s, every factor over s, so one factor last factor over s should be there. Now 1 2 3 in this way, multiplying from 1 to n, we get n factorial. We get n factorial or factorial of n, and the number of s in the denominator is n. So n number of s multiplies and we will get s to the power n. Okay, and the Laplace transform of t to the power 0, and t to the power 0 should be written as 1. Okay, and we already know that Laplace transform of 1 is 1 by s, so the result would be factorial n by s to the power n into 1 by s. So we will get factorial n by s to the power n plus 1. So the result is finally found Laplace transform of t to the power n equals to factorial n by s to the power n plus 1. Okay, so this is the Laplace transform of polynomial function.